Hey, so we're starting a new unit, sequences and series today. It's chapter 9 in your textbook, and I just thought, we could start taking a look at some of this stuff. Um, I will say that again, what's helpful in this unit is to understand what the directions are saying. This might be one of those units where the math is really easy, but if you don't understand what the question is because you didn't take notes on the directions, you might be challenged. Okay, so bell work. Find the next term in each sequence. Okay, so our first one is 3, 7, 11, 15. And our second one is 1, 3/4, 5/9, 7/16. So we want the next one in each of these. All right? Well, take a minute to give them a try. You probably want to pause the video to think about this and see what you come up with. Hey, welcome back. How'd it go? Were you able to have some meaningful and useful thoughts here? Well, I noticed that this went up by 4, and this went up by 4, and this went up by 4. So I thought this one would go up by 4 and be 19. This one's not going up by the same amount. Yeah, and I don't think it's going down by the same amount either. That's really nice when I get that sort of nice linear experience like I do there. But I don't see that happening here. Sometimes, and this is a strategy, sometimes it helps to turn these into a common denominator. In this problem, no, that is not what helps. I will tell you that this one is going to be 9/25. And what I did was I turned the numerator and denominator into two separate experiences. And so I was looking at 1/1, 3/4, 5/9, 4/16. And what I noticed was, well, the tops were going up by the same amount each time. Oops. Sorry, missed something there. Let's fix that. No one will notice. There we go. Tops were going up by the same amount each time. And so if I were going up by 2 by 2 by 2, I should go up by 2 more. Now, what about these bottom numbers? Well, this is 1 squared. This is 2 squared. This is 3 squared. This is 4 squared. And so I went with 5 squared. Now, I think there is an expectation with these problems that you recognize certain sequences, like 1, 4, 9, 16, 25, 36, and so on. Recognize these as coming from n squared, okay? Or 1, 8, 27, 64, 125 as coming from n to the third. These are things that we're supposed to recognize. So if you're not sure about them, you might want to sort of note them down now. Likewise, 2, 4, 8, 16, 32, and so on. These are coming from 2 to the n. 2 to the n. Yeah, 2 to the n. Right. Yeah, so we're going to need stuff like that. Now, in addition to asking us for the next term in each sequence, we might be asked, what's the rule here? And, kind of want to say that these problems are made easier when you provide a little structure and information. So n, a sub n. So n is term number. So for my first term, I had a 3. For my second term, I had a 7. Third term was 11. Fourth term was 15. And we were asked to find the fifth term. And, you know, I can still see, oh, look, these are going up by 4, by 4, by 4. So I want to go up by 4 and get 19. Cool. Now, this is the general case for the nth term. I think of this as what's my rule. If I were trying to describe the rule that would generate every correct ordered pair, I'd want some sort of a sub n. What's the amount? As a kind of like as a function of n, but with respect to n is what I'll say. And you know, a lot of students here want to say that the rule is going to be a sub n equals n plus 4. No, that's not true. See, the n values are these numbers. And if I take that number and add 4 to it, I'm not getting that. If I want a sub 2, I'm supposed to take 2 plus 4. No, that's 6, not 7. There is a way to write the rule like this, but that's called recursive. And I'm going to do recursive with you a little later in this video, but really it's not something I want to do. Instead, what I know about a function when the values go up by the same amount each time is that that's linear. And so whenever I have linear, I can say, what's my rule? And with what's my rule, I know, step 1, find the common difference. And we have a common difference here of 4. Every time these outputs go up by 4. So, in our problem, 4. 2. Multiply the common difference by n. See this n up here? So all I'm going to have now is 4n. 3. Test this rule here by plugging in a value. So if I plug in a 3, I should end up with 11. 3 times 4 is 12, not 11. Okay, so this isn't my rule. This isn't it yet. I have to do something else. I'm not quite there yet. Well, the next thing I'm going to do then is 4, and I know this is hard for many of you, but I want to add or subtract to make the rule work, right? So we plugged in 3 for n. 3 times 4 is 12, but I got 11. So what do I need to add or subtract to make that rule work? I got 12, I want 11. Okay, so I'm going to go with 4n minus 1. And I think for the 5th step, the last step, test another ordered pair. Oops. So before we plugged in a 3 to get out 11, and 3 times 4 is 12 minus 1 is 11. But we want to make sure that this rule works with any of these pairs. So if I plug in a 4, I should get 15. A sub 4 equals 4 times 4 minus 1. Oh yeah, 16 minus 1 is 15. That's great. And so then my rule for the nth term here is 4n minus 1. That's the rule for this sequence, okay? All right, So can I use that same approach for the second problem that we had? Remember, 1 over 1, 3 over 4, 5 over 9, 7 over 16, and then we said, well, these were going up by 2 each time. Yeah, but these aren't going up by the same amount each time. This goes up by 3, this goes up by 5, this goes up by 7. Oh, isn't that interesting? This is going up by these numbers here. Yeah, and while that's interesting, and you could do a whole lot of cool stuff with that in a number theory class in college. Yeah, we're not gonna. I will say, though, that I feel like I could make a rule for the top using this method. This method works anytime I have a common difference. Anytime I'm going to have a linear rule, this will work. And so I could do that on top. And on top, I'm going up by 2. Now, remember, in the last one, we went up by 4, and we didn't do plus 4, we did times 4. I'm going to take that common difference and multiply that common difference times the variable. If I plug in an n value, Mr. Google, I don't see any n values. I know, right? And if only students would write down this, they would have such an easier time relating these numbers to the term numbers. Okay, a lot of people try and do this without this list here. It's much harder. I would definitely encourage you to create this. Even when you're just given a sequence like these 2 bell work problems, turn it into this. Okay, so 2n. I think 2n is my rule because these go up by 2 each time. But if I plug in a 3, I should get 5. 3 times 2 is 6. Oh. And then I have to add or subtract to make that rule work. Well, I'm going to go with minus 1. So 3 times 2 is 6, minus 1 is 5. But when I plug in a 2 for n, will I also get a 3 out? 2 times 2 is 4, 4 minus 1 is 3. Ah, the top is perfect. Now, what about the bottom? Well, this is 1 squared, 2 squared, 3 squared, 4 squared. In fact, 1 squared, 2 squared, 3 squared, 4 squared. And now we've already got a rule for that top, so I'm just really looking for a way to connect the term number with the value of that term number. Okay, so second term has a value of 4. Third term has a value of 9. Fourth term has a value of 16. And so when we come out here to the nth term, what am I going to write? Well, look at our rule. The term number is being squared. The term number is being squared. The term number is being squared. So the term number is going to be squared. And so I'm going to have n squared on the bottom. And so my rule for this data that we looked at, what was it? 1, 1, 3 fourths, 5 ninths, 7 sixteenths. If I wanted a rule for that, this would be my rule. Here's my first term, my second term, my third term. If I plug in a 3 for n, I should have 5 over 9. 3 times 2 is 6. 6 minus 1 is 5. Good. And 3 squared, 9. Perfect. So we're going to do some building. What's my rule? That's probably the hardest part about getting into the Seq and Series unit. There will be some formulas to memorize. You are expected to know things like what are the first 10 values of y equals x squared, or what are the first 5 values of x to the third, or 2 to the power of. Definitely supposed to recognize those. But sometimes, these problems are in fact not anywhere near that difficult, but they are often thoughtful. So let's take a look now. Find the 6th term. Find the 6th term. So we've got 1, 2, 5, 10, 17, and we're looking for the 6th term. Now, again, I'm going to say sometimes it can be really, 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 really helpful to have your term number as well as the value of that term number, right? So a sub 3 is 5. The value of the third term is 5. Then term number 3, the value of that third term number is 5. Okay, so what do you see here? Well, it goes up by 1, goes up by 3, goes up by 5, goes up by 7. And you know, here they didn't ask me for the rule. They just wanted to know the sixth term. So what do I go up by to get the sixth term? Yeah, I'm going to go up by 9. Exactly. 17 plus 9 is 26. Good job. Nice. Hey, will I say that? Oh no, I take it back. Never mind. Thought I was going to say something. Definitely not going to say so. Well, maybe I am. Because, you know, I just noticed this. I mean, don't get me wrong. I'm not changing my answer in any way, shape, or form. But what I noticed was this was 4 squared plus 1. And this was 3 squared plus 1. And this was 2 squared plus 1. Huh. And so I think what I would do if someone made me write a rule here, I kind of want to say n minus 1 squared plus 1. So n, this number, 2 minus 1 is 1. 1 squared, no, that wasn't it. Was it plus 1? Let's try plus 1. N plus 1. So I'm plugging in a 2. No. I'm trying to get this one. Oh, I'm plugging in a 3. No, it really was that. So 3 minus 1 is 2. 2 squared is 4. 4 plus 1 is 5. I'm trying to get this one. I plug in a 4. 4 minus 1. 4 minus 1 is 3. 3 squared is 9. 9 plus 1 is 10. So yeah, I can write a rule for that. But no, they don't want the rule here. Maybe later, but here, they just want to know the sixth term. So what could you come up with for the sixth term of this sequence? 1, 1 plus 2x, 1 plus 2x, plus 3x squared. Good. 1 plus 2x plus 3x squared plus 4x to the third. 1, 2, 3, 4. I need another one. 1 plus 2x plus 3x squared plus 4x to the third plus 5x to the fourth. And then they say, what's the next term? What's the sixth term? Can you do it? Try writing down the sixth term. Nice. Yeah, I agree. 1 plus 2x plus 3x squared plus 4x to the third plus 5x to the fourth plus 6x to the fifth. Cool. Good job. Okay. So there's a lot of thinking about number patterns in this unit. But we'll start gentle. Write the rule for each. And when we do a rule here, I'm saying a sub n equals, and I'm expecting something over here involving n. N is my term number, and this is the value of that term number. So here's my first set, 7, 14, 21, 28. And they want me to write a rule for this. Again, 1, 2, 3, 4, n. These are my term numbers, and these are the values of these term numbers. So when I see a sub 3, that's the value of the third term. So here's the third term, and its value is 21. So a sub 3 is 21 in this problem. But in this problem, we're asked to write the rule for each. They don't want to know a specific value. They want to know what a sub n equals. What's the general case? What's the rule for this data? And long before I ever got finished jabbering on, many of you said, it's going up by 7 each time, Mr. Kukla. I agree. And since it's going up by the same amount each time, I can use that what's my rule technique where I take that common difference and multiply by n. Okay, if I plug in a 3, I should get 21. 7 times 3, oh, that is 21. If I plug in a 4, I should get 28. 4 times 7, that is 28. And guess what? That's my rule. I'm all done. It took 3 steps. All I had to do was identify a common difference, 7, multiply that common difference by the variable, and then test my answer to make sure it works. Okay? All right, so what about this one? We've got 3. Oh no, sorry, this one. 1, 4, 7, 10. So what rule can we have here? Okay, so first term is 1, second term is 4, third term is 7, fourth term is 10, and I want to know what the rule for the nth term is. Yeah, I agree. These are all going up by 3. So we're not going to do that. No, no, no. If I add 3 to this, I don't get that, and I don't get that. So I don't want to do that. Don't do that. Instead, when we see a common difference here, we want to write the common difference times our variable, which is in n in all these problems. Okay, so does this rule work? Well, if I plug in a 4, I should get 10. 3 times 4 is 12, not 10. So remember, step 4 was add or subtract to make the rule work. And I really like this because it sort of really empowers you, the student, to say, well, that doesn't work. I better do something to that to make it work. So we plugged in 4. 4 times 3 is 12, and we got 10. So I think my number was too high, and I want to take 2 away. All right, well, let's plug in a 3, and I should get 7. 3 times 3 is 9. 9 minus 2, oh, that is 7. And so my rule here will be 3n minus 2. Okay? All right. So sometimes our rules are going to be linear, like those were. Oh, hey, one thing. So we just had something like, was it 3n minus 2? Yeah? There's a distinction between y equals 3x minus 2 and a sub n equals 3n minus 2. And the distinction is this. Here's y equals 3x minus 2. We know that this passes through 0, negative 2, and it passes through 1, 1, and it passes through 2, 4, and so on. Yeah? But this one, yeah, n is always an integer value. In fact, I don't think n is negative very often. So I'm going to say usually n is a whole number. And so our this black thing is the graph of that. Well, what's the graph of this? We said n equals 3n minus 2. Well, that graph is this. It's just a bunch of discrete points. There's an infinite number of them, don't get me wrong, but it's just a bunch of points. All these things in between, yeah, they don't exist like they do for the linear function. So while we could make these the same way, and we can treat them often the same way, that common difference really is slope, the reality is that they're not quite the same. This is an infinite list of points, but this is a whole lot more points. This is that whole line that goes forever in both directions. This is, yeah, it's just that. So do understand that connection, but not quite linear. All right, so next set, 0, 1, 8, 27, and so on. And so this is one of those places where, yeah, this went up by 1, but this went up by 7, but this went up by 19. I don't see anything there. And that's okay. I would say that for the people who do 1, 2, 3, 4, and 0, 1, 8, 27. These people have it a little easier, especially if they recognize these numbers. This could be 1 to the third, and 2 to the third, and 3 to the third, and 0 to the third. Now, do we have a way to connect our n value with what we see here? I agree. This base is 1 less than my term number. Okay, so I'm going to have term number 1 less than the term number. All of them are raised to the third. So let's see if that works. If n equals 4, 4 minus 1 is 3. 3 to the third, yeah, that's 27. If I plug in a 3, 3 minus 1, 2, 2 to the third, 8. And so that's it. My rule here, a sub n, is n minus 1 to the third. Okay? All right. Yeah, I want to do some more of these. I think they're good. I think you need more of them. How about this one? 1/2, 8 thirds, 27 fourths, 64 fifths, and so on. And I want to say a couple things here. One, students who write this consistently have a harder time of doing these problems than students who write like this. I think that's very, very interesting from a brain perspective. Like, the students' brains couldn't see here, but could see here. Yeah, not sure what that's all about. And again, I'm going to recommend if you're looking to write the rule, you want to have something here. It's not the next term, not the next term. It's only the next term when they ask for it. And they're asking for a rule. They want something involving some n stuff over here. And if you don't connect these values back to the n's that created them, you're going to have a really tough time finding a rule for this. Okay. So, what do we notice? Well, I notice that I think I want to have one rule on top and a different rule on the bottom. Why? Well, when I look at the tops, I've got 1 to the third, 2 to the third, 3 to the third, 4 to the third. Oh, well, isn't that interesting? 2 was the term number, and I want 2 to the third. I want 3 to the third. I want 4 to the third. And so I think my rule for the top is just n to the third. I take whatever that term number is, and I cube it, and I get the value on top. I take the term number and cube it, and I get the term value on top. Well, that's cool. For the bottom, though, yeah, these are going up by 1 each time. And so do I do n plus 1? No, I don't. I take the common difference and I multiply it by n. Okay, so if I plug in a 2, I should get 3. 2 times 1, yeah, that's not 3. So what do I have to add or subtract to make this work? Well, when I plugged a 2 into what I thought the rule was going to be, I got 2, and I was supposed to get 3. So I'm going to see what happens when I add 1 on the bottom. So if I plug in a 3, 3 plus 1 is 4. There it is. If I plug in a 4, 4 plus 1 is 5. There it is. And so my rule here is going to be n to the third over n plus 1. Any questions about that? Okay, how about 1 3/4, 5/9, 7/16? So this continues. I want you to write a sub n equals. Okay, pause the video, give it a try. Can't wait to see how it goes for you. Hey everyone, welcome back. So, yeah, these don't go up by the same amount each time. Well, actually, I do notice that if I rewrite these, the tops are going up by the same amount each time. Now, I know, and I suspect you know, but maybe you don't. If I take my term number, 2 minus 1, 2 plus 1, no, 2n, sorry, minus 1, 3, yeah. That's my rule for the top, and on the bottom, and then squared. A lot of people don't see how to go from this to that. And I think especially those people, though, really, probably most of you should be comfortable doing this. It could really cut down on mistakes to put your values in here. So we have 1, 3, 5, 7. And this is on top. And on the bottom, we've got 1, 4, 9, 16. So here, I notice I'm going up by the same amount each time. And so this, I'm going to start with 2n, right? It's not n plus 2. That's the recursive one that we haven't talked about yet. But that's going to really suck. So trust me, you don't want to do n plus 2. Because n plus 2 is 4, and I don't get 4 there. Okay. So 2 times n. 2 times 3 is 6. Oh, but I've got a 5. So what do I need to do to 2 times 3 is 6 to turn that value into 5? And remember, I'm only allowed to add or subtract. Now, I'm going to subtract 1. So if I plug in a 4 now, 4 times 2 is 8. 8 minus 1, 7. Or if I plug in a 2, 2 times 2 is 4. 4 minus 1 is 3. So I've got a rule for the top. What about a rule for the bottom? Well, that's 1 squared, 2 squared, 3 squared, 4 squared. Which is why I say you have to know there's an assumption that you're comfortable knowing all the squares or knowing all the cubes. Now, can I relate these expressions back to these n values here? Sure, look at them. Over n squared. I take the term number and square it, and that's that. I take the term number and square it, and that's that. Students who don't write down this row of term numbers, they have a much harder time because they're just trying to essentially create this in their head rather than trying to connect an input with an output, an input with an output. And I recommend connecting an input with an output. Okay. How about this one? 1 over 1 times 2, ooh, it's a negative 1, comma, 1 over 2 times 3, comma, negative 1 over 3 times 4, comma, 1 over 4 times 5, and so on. And, again, I'm looking for a sub n. And my answer over here, almost always, is going to have an n in it. So what's n? Well, n are my term numbers. And if I don't use them, 3, 4, I'm probably going to miss 1, 2 times 3, negative 1, 3 times 4, 1, 4 times 5. Okay? So how can we relate these term values to the term numbers? Do you see a connection between the term number and the value in that denominator? Yeah, it looks like one of them is the same, huh? And so when we come out to n, I'm going to have 1 over, one of them is the same, and this one is one more than that, and this one is one more than that, and this one is one more than that, And this one is one more than that. And so when I come to this one, I want one more than that. And this is almost perfect. Anyone see what's not working quite yet? I have a sign, and the sign is winking on and off. So I need a little sign machine that winks the sign on and off. And conveniently, I can come up with a sign machine that does that. So -1 raised to the power of n. Okay, so -1 to the 1, well, it's going to be -1. -1 to the second power, right? My n is 2. N equals 2, so this is -1 squared. Well, that's -1 times -1, or look, +1. If I do -1 to the third, because n equals 3, I have -1 times -1 times -1, which is again -1. And so when the signs go negative, positive, negative, positive, that's my little sign changing machine. But if my signs went positive, negative, positive, negative, I would use -1 to the n plus 1, or -1 to the n minus 1. Now, what am I supposed to do with this sign changing machine? Well, remember with this sequence, we said the rule would be 1 over n plus 1. But our sign was winking on and off, and this is the little machine we want to create the signs that we had in ours. And so I'm going to do -1 to the n. You could put it there. You do -1 to the n times 1 over n plus 1. That would be fine. I just need to have this somewhere on top. Out in front works. I just don't want this to fall into the bottom. No, I could even have it in the bottom. I think, though, my eye would prefer on the top, because I only see ones and -1s on the top, and the negative symbols on the bottoms. Okay? So, yeah, use that sign winking machine. Whenever you need a sign winking machine, use one of these. If the pattern is minus, plus, minus, that's your sign winking machine. If your pattern is plus, minus, plus, minus, use one of these. -1 to the n plus 1, or -1 to the n minus 1. And that will generate the appropriate SIGNs when you have alternating in that other pattern. So, can you do this one then? 1 times 3. -1, 2 times 5. 1, 3 times 7. -1, 4 times 9. And so on. Und so weiter. So, yeah, what can we do here? What do you see here? Well, first, I just want to give a moment of thanks because this is where the problem really starts. And I don't have a clue how to write a rule for this. That goes up by 7, and that goes up by 11, and that goes up by 15. What? This is 3 squared for the second term. This is 3 times 7. This is plus 1. So I'm kind of at a loss. And what I'll say here is, when I start, maybe I'm not starting here in this form. Maybe the first thing I'm supposed to do is look at this data and say, oh, I wonder if there's a way for me to not simplify this, but break this down. And so they said 1 times 3, 2 times 5, 3 times 7, 4 times 9 to make these values. Now, I agree. There are more ways to get 10. How did they know it wasn't 1 times 10? How did they know that this wasn't 1 times 21? How did they know this wasn't 2 times 18 or 3 times 12? Why is it 4 times 9? Well, it turns out that whatever the rule is, it should work for all of these. And so a rule that's going to work for this, yeah, it doesn't work for that. So, yeah. But I can come up with a rule for each of these that does work. And yeah, looking at this in unfactored form, yowie, that's tough or tougher. And so maybe the first thing I want to say is, break these things down. Got our first term, our second term, our third term, our fourth term, and we want the nth term. And we're given 1 times 3 times 5. Ooh, there's a negative 1 on top there. Positive 1, and we have 3 times 7. And we have negative 1 4 times 9. All right, so what's our nth term going to be? I agree. I see these values going up not only by the same amount each time, but I see these values are the same as this. So when I come to write the nth term, first is n. This is this, this is this, this is this, this is this. So this must be that. And that's what I've got here. Now, there's this other one, and these do go up by the same amount each time. So I'm expecting a 2n plus or minus something to make it work. Well, let's see. If I plug in a 4, 4 times 2 is 8. I need 9. If I plug in a 3, 3 times 2 is 6, but I need 7. If I plug in a 2, 2 times 2 is 4, but I need 5. So what do I have to add or subtract to make that part of the rule work? I'm going to have to add 1. And let's see if that works. If n equals 4, 4 times 2 is 8, 8 plus 1 is 9. Hey, that's 9. Well, that's nice. Times 4, we'll look at our n code. So we're going to get 4 times 9. Now the only thing we haven't taken care of yet is this sign winking on top. Does this work? If I plug in a 1 here, do I get positive? No, I get negative 1. If I plug in a 2 here, negative 1 squared is negative 1 times negative 1, which is positive 1, but I need a negative. So this isn't the right machine. You want either this one, n plus 1, or this one, n minus 1. So if I plug in a 2 for n, 2 minus 1 is 1, negative 1 to the 1, yep. If I plug in a 3 for n, 3 minus 1 is 2, and negative 1 to the second power, well, it's negative 1 times negative 1, or positive 1. So I think this is perfect for generating our rule. Negative 1 raised to the n plus 1 on top. And on the bottom, we have n, and we have a 2n minus 1. I think it's 2n minus 1. Is it 2n minus 1? 2n plus 1. Yeah. And there's our rule. There's n equals. Now, the nice thing about building these rules is someone could say, hey, can you tell me the value of the 17th term? Sure, I just plug a 17 in there, a 17 there, and a 17 there, and I know what a sub 17 is. Okay, that's very powerful. Now, next, find the first 4 terms. So what happens if instead of being given a sequence, we're actually given the rule, a sub n, 3n minus 2. And the directions here, find the first 4 terms. Okay, so we know a sub n equals 3n minus 2. 1, 2, 3, 4. So if I plug n, I plug in a 1 for n. 3 times 1 is 3. 3 minus 2 is 1. If I plug in a 2 for n, 3 times 2 is 6. 6 minus 2 is 4. If I plug in a 3 for n, I'm going to have 9 minus 2 is 7. And if I plug in a 4 for n, I'm going to have 12 minus 2 is 10. So these are the first four values. And that's it. That's all I have to do is just plug in the numbers 1 to 4 there. All right? Yeah, there's another way that they could write this. They could say something like find a sub 1, a sub 2, a sub 3, a sub 4. That's a sub 1, that's a sub 3, and that's a sub 4. The value of the third term, the value of the fourth term. Value of the fourth term is 10 because 3 times 4 is 12, 12 minus 2 is 10. Oh. So, I think we have a sense of how to do this. Find the first four terms. Find the first four terms. And here's a little general case. This 1 over 2n. Okay, so we find the first four terms. Yep. So if n equals 1, 1 minus 1 is 0, 0 over 1 is 0. The first term is 0. My second term, 2 minus 1 is 1 on top. 2 times 2 is 4 on the bottom. If I plug in a 3 for the third term, 3 minus 1 is 2. 3 times 2 is 6. You could certainly reduce that to 1/3, or you don't have to. I mean, in some situations you want to, in some situations you don't want to. And the value of the fourth term. 4 minus 1 is 3, and 4 times 2 is 8. And I could even extend this, because like this looks like it's going up 2, up 2. If I go back, then I'm going to go down 2. So, that's 2 times 2, that's 2 times 3, that's 2 times 4, so this would be 2 times 1. Yeah, I can extend this pattern backwards as well. Though they usually want the first four terms where n starts with 1. Okay, and then 1, 2, 3, 4 on the bottom. I'm plugging in 4 times 2 is 8. Okay, 3, 3, 2, 3, third term, 3 minus 1 is 2, and 2 times 2 is 6, and I don't get 3 A's. What am I missing here? Oh, I guess that's wrong. That's what I'm missing there. There we go. So I'm plugging in 1. I'm plugging in 2. I'm plugging in 3. I'm plugging in 4. Good. Unsimplified. So that should be 1/2. How does that become 1/2? Well, n over 2n minus 1 over 2n. This is going to simplify to be 1/2 minus 1 over 2n. So when n was 2, minus 1/4. Yeah, I'm not quite sure about that. Yeah, good. I'm not going to check. Instead, I'm going to press on to this next one. A sub n equals -1, n plus 1 times n squared minus 1. Will you please write the first four terms out there? That would be fabulous. Okay, so n is sub n 1. When I plug in a 1 for n, 1 times 1, 1. 1 minus 1 is 0. Kind of don't care what's here, because thing times 0 is going to be 0. But if I plug a 2 in, 2 squared is 4. 4 minus 1 is 3. And if I plug a 2 in, 2 plus 1 is 3. -1 to the third. -1 times -1 times -1. That's going to be -1 times 3, right? Because we plugged in a 2. And so you might want to write that as negative 3. I'd be okay with you writing it as negative 1 times 3. But yeah, I agree. Negative 3 is better. If I plug in a 3 for n, 3 squared is 9, 9 minus 1 is 8. And what about plugging in a 3 over here? Well, 3 plus 1 is 4, and negative 1 times negative 1 times negative 1 times negative 1, that's going to end up being positive 1. And so I get positive 8 there. Okay, and will you try the fourth one? Remember, this is the rule we're working with, and I want to know the value when the term number is 4. So, can you help me find that? Hello. So, if I plug in a 4, 4 squared is 16, 16 minus 1 is 15. And here, when I plug in my 4, 4 plus 1 is 5, negative 1 to an odd power is negative 1. And so I've got negative 15 there. So our values, 0, negative 3, I think this is 8, and negative 15. Coolio. Next, let's deal with that recursive stuff. Recursive. The next term value depends on the current value. Okay, so what does this mean? Well, it means, for example, if a sub n equals 3 for n equal to 1, but 3 minus a sub n minus 1 for n equals 2, 3, 4, 5. And the directions here say find the first 5 terms. Okay? Now, clearly, when n is equal to 1, I get 3. So a sub 1 equals 3. That's what I take from this first part, that a sub 1 equals 3. Aha, when I plug in a 1, the value is 3. Now, if I'm going to plug any of these other numbers in, like 2, 3, 4, 5, yeah, I have to use this piece here. So how do I understand this bunch of symbols here? Well, a over n minus 1. N is the term number. So for the second term, I'm going to set n equal to 2. Okay? And here, I'm just trying to understand that. That says a sub n minus 1. In our problem, the next term is 2. So we would have a to the 2 minus 1, or a sub 1. Well, a sub 1 is 3. Oh, okay. So it looks like I'm using the last number somehow. And how am I using the last number? Well, look here. 3 minus the last value. Well, the last value is 3. And I want 3 minus that last value. 3 minus 3 is 0. Okay. What about plugging in a 3? Okay, so for 3, I'm using this piece. And here, I'm going to have a sub 3 minus 1. Well, a sub 3 minus 1 is a2. And a sub 2, that value was 0. So I'm going to have for the value of that doesn't make sense to me. Sorry. Hold on. Look at that again. A sub n minus 1. The nth term is 2. 2 minus 1 is 1. A sub 1. 3. 3 minus 3, 0. If I plug in a 3, a sub 3 is a sub 3. A sub 3 is 3 minus a sub 3 minus 1, a sub 2. A sub 2 is 0. I want 3 minus 0. If I plug in a 4, well, I want a sub 4 minus 1. And that's going to be a sub 3. A sub 3 is 3. And so now I've got 3 minus 3 again. And I get 0. Okay, plug in a 5. So I'm going to have a sub 5 minus 1. That's a sub 4. And I want to say 3 minus that number. Yep, and I get 3 again. All right, so there's that. Recursive. And maybe we can describe it. Instead of trying to describe using the notation, maybe it would be better to say this. If this represents the value of the current term, then these symbols here mean the value of the term before that term. Like, if this is, I want the value of the first term, then this is going to be 3 minus the value of the last term. 3 minus the value of a sub o is what I'd be looking for. Okay, let's do 1 or 2 more of these. These are very popular on ACT. So we've got a sub n equals 5. And on the bottom, 2 a sub n minus 1, 4 n equal to 2, 3, 4, 5, and 5, 4, n equal 1. All right, and remember the directions here will find the first 5 terms in the sequence. So, is this division? No, this is just piecewise. Okay, so a sub 1, right? I mean, I'm going to have 1, 2, 3, 4, 5. We need to have these first 5 terms. And here I want an a sub n. If I plug in a 1, I get 5. If I plug in a 2, 2 minus 1, that's 1. And so I want the value of the first term, 5, times that 2 that's out in front. Okay, if I plug a 3 in, so 3 minus 1 is 2. I want the value of the 2th term or the second term, and that's 10. But don't forget to multiply that by 2. And what about a sub 4? Well, I notice in each of these cases, I'm taking the last value and multiplying it by 2. I took this last value, multiplied by 2, got this value. I multiplied by 2, I got this value. I multiply by 2, multiply this by 2, and subtract 1. And here, I'm going to find the value of the 5th term. It's 4. That's this one times 2, which is 78. All right. One last one. A sub n equals 2, 4, n equals 1 and 2, and 3 a sub n minus 1 plus 2 sub 2 a sub n minus 2. And that's going to work for n equal to 3, 4, and 5. And here I want to find the value still of the first 5 terms. Value of the first term is 2. Value of the second term, when n equals 2, the answer is 2. Oh. Okay, so what about the value of the third term? Well, this is how I read this notation. I want 3 times the value not the third term. I want 3 times the value of 3 minus 1. 2, I want 3 times the value of the second term. Second term has a value of 2. 3 times 2 is 6. Plus, I want 2 times the value, not of the last one, not of a sub 2, but 2 turns ago. Well, 2 turns ago I was here, and my value would be 2. So I want 2 times 2 plus 3 times a sub 1 is 2, 6. Got lost in it. Sorry. Okay, 6, 2, 1, 2. Sub n minus 1. Sub n. So n minus 1 is 2. A sub 2. 2 times 3 is 6. Plus a sub 4 minus 2 is 2. 2 times a sub 2 is 2. Huh? Earth. 2 minus 2 3. Yeah, good. 1 a sub 1 is 2 times 2 is 4. I get 10 in. And if I plug in a 4, 3 times the value not of the fourth term, but the third term, so that's 3 times 10. And for this one, this is the value 2 terms ago. So I'm doing the third term. This is the first term. Okay, so a sub 4 minus 2 is 2. A sub 2 is 2 times 2 is 4. So we've got 6 times, oh, there it is, 6 times. Oh, I missed that. That's good. 4, I'm plugging in 4, 2 terms ago for 4 is a sub 2. A sub 2 is 2. Okay. Times 2, 4, 4 plus a sub 3, 10, 30. And I plugged in a 4. 2 times 2 is 4. Yes, plus 10. 40. Alright, what about that fifth term? Well, I do see a pattern here, but it's a recursive pattern, right? See how the value of the fourth term depended on using that value of the third term? And the value of the third term depended on me having the correct value of the second term. And to find the value of the second term, well, I just use that. But maybe I would have to do that as well. So I guess I want to say, what happens if someone asks me to find a sub 97? Well, this recursive method sucks for something like that, because in order to find a sub 97, I'm going to have to find a sub 96 and a sub 92, and that means to get a sub 97, I have to go all the way back to a sub 1, build the model, and then bring it all the way back to a sub 97. So recursive, not my first choice. That's always going to be either, as it was here, something I was directed to practice, or the last thing on my list. Okay. All right, I want to dally just for a couple moments on one last topic. I know this is going long. I'll try and be brief. 3 factorial. This is the factorial symbol, which means 3 times 2 times 1. And 4 factorial, well, that's 4 times 3 times 2 times 1. Or we could even write it as 4 times 3 factorial. Yeah, because there's 3 factorial times 4. Okay, so can you simplify this? 10, 9, 8, 7, 6, 3, 2, 1 over 8, 7, 6, 4, 3, 2, 1. So what happens? And so I'm thinking about, I'm thinking that this, I could start taking the bigger one and breaking it down. But as soon as I get to that, I could stop because then they're the same and I just throw it away. So my answer here is 90. Okay, will you do this one? 25 factorial over 23 factorial. 25 times 24 times 23 factorial, because this is going to continue. And on the bottom, 23 factorial. So all I have to do is multiply those two numbers together. 25 times 24, and I'm going to get 600. How about this one, though? I have n plus 2 factorial over n factorial. Well, what did we do here? We started with this number, and then we subtracted 1 from it, and we subtracted 1 from it. So I'm going to start with this number, and I'm going to subtract 1 from that. N plus 2 minus 1 is n plus 1. Okay, n, and now n factorial over n factorial. And so my answer is just going to be this. You're more than welcome to turn that into n squared plus 3n plus 2. But I think this is fine also. So, can you do it? How about this one? N plus 1 factorial over n factorial. I agree. Because n plus 1 times, I subtract 1 times, and so on. And on the bottom, I'm starting with that, and I'm going to subtract 1 from that, and so on. So those, and those cancel, leaving me n plus 1. Okay, how about this last one? We've got n plus 3 factorial over n minus 1 factorial. So always start with the bigger one. Doesn't matter if that bigger one is on top or on the bottom. Okay, so this pattern would continue, right? Subtract 1, subtract 1, subtract 1. And once I get here, this is that. And so this is my answer. Except, yeah, no, that is my answer. All right, well, welcome to Sequences and Series. Guess what? We're going to do some more of this tomorrow. And if you need more practice problems, don't hesitate to let me or Mr. Paz know. Take care, everyone.